One of the points that I wanted to highlight in the book is there is a section where Giancoli is just wrong, and that's dealing with inductor resistor circuits, and we get into AC circuits also. Now, we will come up with the exact same formulas that he comes up with, but I don't want to take you down the path of thinking that the way Giancoli is doing this is correct. And here are the reasons that it's not correct when he does his analysis. First, magnetic fields are not conservative. So when we integrate around a closed path, the result is not zero, like we would have with a conservative force or field. Second, Kirchhoff's voltage law does not apply to currents changing over time in a presence of a magnetic field. The third is that there's no potential drop across an inductor. It's an induced potential. It's not a voltage potential over like we had a resistor or that we could calculate with an inductor. This is an induced potential that is different from a potential drop. And this induced potential is fighting the change. So here we have Lenz's law. And when we read read a voltage on a voltmeter, it's the induced potential that the inductor is making to cause that reading in the voltmeter. There's a circuit and it is creating a loop, and so the inductor is giving the induced potential reading to the meter because of that interaction. And the last part, we have to use Faraday's law to solve these problems. And so this relationship that we brought up last chapter, we're going to talk about this more in chapter 31, but this is the basis for solving circuits. So if we integrate this electric field and along this path, then that has to equal the change in flux inside of the circuit. So let's take an example here. Of a battery, a resistor, and an inductor. So we have resistor and an inductor. So let's say that we have this voltage potential. So I'm going to have a difference in potential here. So I'm going to have an increase. I'm going to have a decrease in a potential here. And as I go around, there is no electric field. No electric field in the inductor. The wires. Write that a little bit better. Inside those wires, there's no electric field. The electric field cannot exist inside of a conductor. So, because of that, we aren't going to be looking at any electric field there. So the only electric field exists in the potential, this V, this battery or cell, and the electric field inside the resistance, because the resistor creates a potential difference. And the inductor is conductor in the inductor. Sounds kind of crazy. But we can't have an electric field inside the conductor. And the magnetic field will exist inside this coil, but if I were to wrap around, unwind this coil, then the magnetic field is going to be going through this loop in some way. And that is how this gets related back here. So even though the magnetic field actually exists only inside the inductor, if we were to string it out, the magnetic field would go through the loop, and it's that same magnetic field that gives us the use of Faraday's law to solve these circuits. So it's very important that you understand when you read Giancoli, he's wrong. I would prefer you would stay away from that section where he talks about this, and we'll solve the circuits the correct way in the next few examples.